Hi everyone. So today's presenter is Emma Thomas from Northumbria University. Emma is a PDRA working with Tom Stallard and the rest of the team at H3 Plus to observe and analyze the infrared emissions of the outer planets. She completed her BSc in physics, her MPhys in physics, and her PhD, all at the University of Leicester, with her final thesis titled Infrared Observations and Investigations of Uranus's Aurorae and Ionosphere of Uranus. The research focus has continued into her postdoc position, using a mix of ground-based data and JWST to unlock the mysteries of our ice giant neighbours. Today's presentation is titled Keeping It Cool. Does solar wind affect the short-term temperature changes in Uranus's ionosphere? So Emma, I'll let you take it away.
Awesome, thank you, Gemma. So hi everyone. I am going to be discussing a little bit on what I've been working on, but I will, before jumping into it, try and give a better idea of kind of why we're doing this and what I'm hoping to achieve from it. But equally, any feedback or any suggestions from people will always be very welcome, and hopefully I can get that at the end. So, first off, talking about Uranus, or specifically kind of the atmosphere for Uranus. So Uranus itself is a very funky place. We're out at about 19 AU, so 19 times distance from the Sun in comparison to that of Earth. Unlike Jupiter and Saturn of the outer planets, Uranus is a little bit smaller, only about 4 times the radius of that of Earth, with 14.5 mass in comparison, so slightly bigger. Rotates over about 17.24 hours, plus minus a couple of decimal places. But planet is a very unique in the fact that, well, unique comparatively to that of Earth, but not so much that of the other outer planets, with its atmosphere predominantly consisting of that of a majority of hydrogen, about 16% of that of helium, and a 3% that of methane. It is that 3%, which is different in comparison to that of Jupiter and Saturn, which produces its very blue color that you're seeing here on the right-hand side from Voyager 2. That's one of the photos that we got back in 1986. And to clarify on that, is literally the only time we've ever gone to investigate Uranus with a instrument. So a lot of our data that we understand in terms of its orientation, its orbital period, came from data and instruments from back in 1986. So there's still a lot in terms of understanding for this planet that we have. Main kind of parameters for the planet is when we consider that of the axis tilt. So what I mean by that is basically how inclined is it in the Sun-planet plane. It is essentially rolling on its side, which you're seeing here on the right-hand side. That's the blue vector, that's the rotational tilt. This means because of its rotational tilt and its position in the solar system, a year at Uranus is in fact 84 years at Earth. This means because first taking observations back in 1986, we actually haven't seen a complete Uranus year at the moment, meaning we still have a lot more data that we need to take, which, is basically means hopefully the job that we're doing at the moment is at least guaranteed for a good couple of years onwards. To add to this mystery, Uranus has its own magnetic field, which produces its own magnetosphere, but it's incredibly unique when comparing that to Earth, as well as Jupiter and Saturn, and that's because of the additional 54-degree tilt from the rotational axis, so that's this M vector here. This results in not only a plasma sheet that flaps essentially from both the north and south hemisphere, as you're seeing here on the right-hand side, but it also means we have a very asymmetric aurora at the planet, with a northern aurora that's almost, well, more than double the size of that the southern aurora. In total, though, it's a very unique, weird, and wacky world, meaning there's a lot of questions we have, and as we say at the title, not a lot of answers we have with it. When completing our research looking at infrared emissions of Uranus, we're specifically looking at an atmospheric layer of a planet known as the ionosphere. For all of the outer planets, this is typically produced with, at least for infrared, through the ionization of the hydrogen mix in the planet's atmosphere. Sorry, needed to highlight that. How these are produced, or how the H2 plus is produced, it can be due to two dominant features at a planet. So on here on the right-hand side, we have, I think this is the southern aurora for Jupiter. So wrong way around, but we have two key dominant drivers that produce this infrared emission. We have solar EUV photons. These typically will collide with a planet's H2 consistently, basically over the sunlit side of the planet, dropping off basically in the nighttime, whereas the energetic electrons are spatially dependent on where magnetic field lines intersect with a planet's atmosphere, so basically where there's open magnetic field lines. Hence, we typically expect very strong emissions at the aurora and everywhere else there to be pretty consistent, though different studies have seen there have been some very minor variability, certainly at Jupiter and, well, at Jupiter with Saturn unknown at present, I believe. So, an ionosphere itself is typically the layer that is consistent of a majority of ions. For Earth, that typically occurs between, I'm going to remind myself, I think that was between 60 to 300 kilometers, I think. Again, don't quote me on that. It's slightly different for that of Uranus, however, we are much further up. Paula presented some of her work earlier this year, which highlighted that the majority of where this H3 plus density sits at is peaking around between 1,000 and 2,000 kilometers above the surface of that of Uranus. So that's predominantly where a lot of these measurements, when we're looking at infrared investigations of Uranus, will come from. So the very basics of how we go about looking at infrared emissions and how we, or what we investigate, kind of been covered very roughly there. But what have we done? What is the history of looking at these emissions in general? Well, infrared emissions at Uranus first started back in the early 1990s, where they found temperatures up to 720 Kelvin for the H3 plus. For the fact that H3 plus, sorry, I see there's a chat message. I presume I can answer questions at the very end. Just double checking.
Yeah, you can come back and answer
Cool.
the question.
All right, sorry. The beginnings of investigations was at 720 Kelvin. H3 plus itself, because of it being a dominant ion within the ionosphere and it thermally equalizing with its surroundings, we can assume at least the ionosphere and the thermosphere it sits around these temperatures. One of the really interesting things that we've seen is this long-term trend at Uranus, where since the 1990s we have seen almost a halving of the temperature all the way down to about 400 Kelvin at current time, I think, yeah, 2025, 2026, with no real explanation as to what is causing this, or at least no confirmed explanation. Additionally, the short-term variation has been investigated back in 2011 with Milan et al. In 2013, where they identified temperatures varying from the high 400s all the way up to the mid 500 Kelvin over only a 2-3 day period. Again, with no real understanding as to what the cause for these are, or what is it that's causing the ionosphere to suddenly jump in these energies. current theories kind of vary. So originally, it was proposed that perhaps this was a solar cycle event, that with the fluctuation of a solar cycle over the 11-year period, we should expect the temperatures to pick back up. As you can see, hopefully, if I put this, there we go. You can see basically within this solar cycle, and then following on from the second one, there isn't this kind of sinusoidal relationship. So that kind of very quickly got thrown out. Instead, we looked on a more longer scale. So originally that was looking at the peaks of a 42-year period, so half a rotation around the sun. However, again, we have continued to see over this period a decline. So that has now left us at a point when considering seasonal variation that we're looking over a complete period of Uranus, being an 84-year period, where we expect hopefully temperatures to rise back up in 2030. Now, at the moment, that's going to require an extra, 4 years to wait. So that wasn't an area that I wanted to try and go down just yet because I haven't got a time machine. Hopefully in the future we can. So instead, I wanted to focus more on kind of things that I could investigate specifically. So instead, we have auroral temperature decline. So what I mean by that is at Jupiter, we've seen that temperatures at the northern aurora and southern aurora from O'Donoghue back in 2021 were almost twice that of the temperatures at the equator of the planet. Additionally, an event that they observed back in, I want to say 2017, January, they saw a heat wave from the northern aurora basically emitting out towards the equator with a speed of about 600 meters per second, strongly suggesting that the heat from the aurora is able to overcome the Coriolis effect of the planet and is able to effectively act like a really extremely warm heater for the planet. So could the same thing be happening at Uranus? Well, unfortunately, from James Webb, that's what you're seeing here down below with Milan in 2025, saw that temperatures at Uranus are predominantly very tight-knit in the sense that where we see aurora, that's where you're seeing these white dots on the left side, as well as over here dragged out at the equator, we see minimal temperature change. I think, in fact, only maybe like a couple, like 10 Kelvin, 20 Kelvin at most, suggesting that at least if there are global differences that are happening on the planet, it is not the aurora that is the main culprit. So, that idea put to one side. So, instead, we consider another variable. Perhaps it is that the H3 plus altitude that we're investigating is changing. We know from Paola's investigations in 2023 that this peak was back at 1,000, 2,000 kilometers up. However, if the peak were to increase in altitude due to Uranus's exosphere being incredibly much hotter, up to about 800 Kelvin, as saw by Voyager 2, we would expect with an increase in altitude that those temperatures will perhaps increase, and vice versa if you decrease in the altitude. So perhaps it is the altitude of H3 plus that has been decreasing. Unfortunately, that kind of ties in with the seasonal variation where we need a time machine to go back to look at the altitude profile back when things are much hotter. So again, that's kind of out of my hands. So then that leaves us to the final culprit or a final theory that's been put forward very recently, which is the consideration of the effect of solar wind. At Uranus, one of the main assumptions that we have is that, unlike that of Jupiter and Saturn, Uranus is predominantly solar wind affected. And what I mean by that is very similar to that of Earth. We don't see any dominant ion sources from Uranus's moons, and that the rotation speed is much slower in comparison to that of Jupiter and Saturn to that effect, that we expect there to be solar wind reconnection at Uranus. As bizarre and as weird and wonderful as that magnetic field is, we expect that to be one of the reconnections methods for Uranus. So, On that assumption, we then take that perhaps it is the pressure or the kinetic power on Uranus's magnetosphere that could be affecting the temperatures of the thermosphere and the ionosphere. And this was a theory that was investigated by Masters in 2024. They identified that over the 30 to 40 year period of measurements that the kinetic power declined from about 4 terawatts down to 2 terawatts over the same time that we saw a halving of the temperature, showing at least there was a linear trend between the two, with I believe, a 0.7 Pearson coefficient, strongly suggesting that these two could be correlated to one another, and that it is the, if I remember correctly, the power incident on the magnetosphere that was actually causing the magnetosphere's radius to inflate due to the declining pressure on the magnetosphere. Ugh, sorry, mouthful. However, to add to this confusion, a year later, Jasinski et al. Highlighted that since the solar cycle of starting from 2009, there has in fact been an increase in the kinetic power from 1.7 up to 2.2 terawatts, I want to say, if I remember those numbers correctly. Whereas we have seen temperatures continuously decline from about 570 down to the 400 Kelvin point, showing that at least up till the cycle 2009, that this assumption that the solar wind was dictating the temperatures couldn't be correct. So it leads a lot of theories of like, it could be, it couldn't be. What I wanted to do, however, was, and it was something that we hadn't looked at specifically, was using these solar wind parameters to dictate whether on a shorter scale, so that's going back to that 60 to 70 Kelvin difference that we've seen over maybe a couple days, if perhaps the solar wind is effective in these much shorter ranges in comparison to the much longer ranges. How did we go about doing this? Well, there is a lot of past data that could be investigated, but I wanted to try and use the current data where we have much colder temperatures to identify if there was any correlation with the dynamic pressure of the solar wind. So, how did we go about doing this? Well, that's using ground-based telescopes such as IRTF. That's what you're seeing here on the left-hand side. IRTF is specifically an infrared telescope, which is a 3.2 meter telescope dish up at about 4.2 kilometers in, I guess, altitude of sorts. It's on top of Mauna Kea in Hawaii. Brilliant place. I would always recommend it if you can. I know Hawaii prices are not exactly the cheapest here, but if you ever get a chance, totally recommend. Over the course of about 2 years, we would place a spectrometer slit, so that's what you're seeing here in the red, over Uranus to observe basically the whole disk so we could get global averages. Hopefully, there we go, is a video representing exactly what we saw on the night. So what you're seeing here is you're seeing Uranus along with the actual rings just around it, where this black bar is the slit. That's where we get our data. Surrounding it, we then have the moons. I don't know off the top of my head which ones these are. I want to say that's maybe Miranda. That's probably Titania, and one or two of these might be Ariel. That's as best as I can give you at the moment. But we have basically, I think, a good 20 to 30 dates where basically we repeated this, and we would take stretches of what are known as spectra. That's basically looking at the amount of light we get at specific wave points, and it kind of looks like this below. How we produce this data is basically each slit is placed from left to right, increasing in wavelength from the bottom to the top as well. Sorry, not how I'd like this to be, but unfortunately that's just how we get the data. And because H3 Plus is investigated in laboratories at Earth, we know the exact wavelength position that we should expect H3 Plus signals to occur. which is these 3 points, which are known as the Q1, Q2, and Q3 emission lines, with Q basically, this is getting into the quantum mechanics side of things, basically being when there is no change in the spin, I want to say. There's no change in the J vector, but again, that's getting a bit too much. Basically, these are the strongest emission lines that we can get for Uranus. What we then do is we will extract, taking basically a, how to put it? If I go back to the previous one, we will then look in the y-axis, we can then extract out a wavelength, a spectra with wavelength to give us the following spectral radiance versus wavelength. Here we can then identify these specific emission lines. So here are 3. Technically, there's a 4th one just hidden here on the right-hand side of 30, but unfortunately, sometimes the noise with this data can mean that it's quite hard to tell that. So typically, we mainly focus with Q1, Q3, and Q2. What we can then do is we use our software known as Happy. Happy basically is given all of the quantum parameters, so that's kind of your J's, your energy levels, your rotations, and whatnot. A lot of in-depthy things, but basically the gist is if we compare the heights of these emission peaks with one another, we get an idea of what their temperature is from one another from that ratio. Comparing these ratios together, we can then basically refine what the temperature is and give us a much better error, which is why stuff at James Webb, for instance, which covers a multitude of emission lines, can get down to some really scary errors. I say scary good errors of like 1-2 Kelvin. It's absolutely nuts. I'm very jealous. From these parameters then we can then compare several dates with one another, and in this investigation we covered over about 26 observations, unfortunately, due to weather. Wasn't always successful, as you're seeing here on the right hand side, or due to instrument errors. Unfortunately, the kind of yin and yang of getting to use ground-based, but we at least got 20 nights where we were able to investigate both the temperatures and then compare these to solar wind parameters. So first off, how did the ionospheric temperatures look? Well, over the 550 days we investigated, we certainly saw a lot of variability. Specifically at the start of the investigation, which was in August 2024 to just the beginning of September 2024 as well, where we saw temperatures vary all the way up to almost 500 Kelvin and all the way down to about 360 Kelvin, showing at least a good 130 difference. Though this is a little bit higher than what we've seen in the past, this same magnitude had been seen by Millen in 2013, especially at the order that we were seeing it, which is over maybe 3 to get this right, 12 days. Variability. So certainly incredibly interesting that we were seeing this variability. Second of all, what we're seeing here in the green is the long-term cooling trend. So that is, if I rewind very quickly, taking back to looking at the, there we are, the sinusoidal wave, which is including the seasonal variation. So what we expect the temperatures to be with this seasonal variation, which is an 8 Kelvin decline per year. So that's been included, at least what we predict the temperatures to be like at this point. So you can see that there are a mixture of some of the temperatures will agree with some temperatures actually falling outside of this range, perhaps suggesting that there is specific points where we're seeing these hikes or even declines in temperatures, and perhaps these are being affected by that of solar wind. So, how did we do this comparison with solar wind? Well, there are a lot of models with solar wind. You can use Tau model, you can use Hux model, you can use, I think it's the two-dimensional swim model, and a good couple of others. The struggle we have with Uranus is that not all of these models are made in mind to go all the way out to Uranus. with the fact that with only having a single mission, Voyager 2 going out, there's a very distinct lack of data to investigate solar wind out at these parameters. At present, I've only done the solar wind comparison with Tau et al., though I'm currently in discussions with the team that work on HUXT to look at some of the investigations on there, and hopefully in the future continue this out with further models. But for this moment, we're predominantly focusing on the Tau one-dimensional model that's discussed in Chihiro's paper in 2005. The Tau model, which is predominantly using Earth observations from Omni over a 1-hour period to propagate this out using the, I believe, the radial distance out to Uranus to try and give us an approximation of solar wind at specific times. Now, the Tau model itself contains an uncertainty of up to about 3 days, which is why we have this 1-week window, and to account for the fact that I've forgotten what they're called, but they're specifically high energy particles that affect outside of the 10 AU radius, which can cause an additional not decline, an additional slowing of the solar wind. So we have then included this 2-week window on the right hand side to try and account for any discrepancy in the solar wind due to the errors within the models and other parameters. We then investigated or compared with that of the medium and the maximum solar wind dynamic pressures, and this is because we want to investigate if perhaps the background or the usual solar wind dynamic pressure was being the main driver of the effect on the temperature, or perhaps that there was a peak in the solar wind pressure such as a CME or perhaps a CIR, that's a co-rotating interplanetary region, if I remember that correctly, were perhaps the main drivers of the temperature, and investigate both these points. So, getting on to the actual figure itself, so that's here on the right hand side. Overall, we see with our data a very weak correlation, almost zero correlation when considering the Pearson coefficient with that of solar wind conditions in comparison to the temperatures. Whether this be with the medium or whether this be with maximum, we still see that of 0. One additional factor that I did want to include with this data was the fact that the data wasn't adjusted with the effect of the long-term cooling that's been occurring over the 2 years. So that's in this next part, which is a very, very small change, where these temperatures were then readjusted to counterbalance the cooling effect that had occurred from 2024 to 2026. However, even with this effect in mind, we still see Pearson coefficients across both medium and maximum over 1-week windows and 2-week windows, which were incredibly close to 0, strongly suggesting that the solar wind, at least over this 550-day period, is not the leading cause for the change in temperatures that were being investigated over this range. However, we have highlighted that we're looking at short-term variability, and we want to try and investigate over a period similar back in 2011. So what we then did was we looked at 2 areas of the observations. In fact, if I go back just a little bit, there we go, where we saw incredible differences in temperatures. So this was looking at this August-September time that you're seeing between 200 and 300 days, and then between 700 and 800 days, where we see almost minimal temperature differences from one another in January 2026. Why is this? Is this something due to the solar wind, or were there differences in solar wind conditions? So, first one in August and September, which contains a sample size of about 8 observations, contains the highest variability in the temperatures. Pretty much that 130 Kelvin difference that we saw before is predominantly from this data set. The mean and the medium are slightly different from one another, which is different than the whole data set from before, perhaps suggesting some of the higher temperatures that we're seeing on this sector could have been affected or have certainly affected the data itself. What is incredibly interesting with this data set, and is something that I want to kind of consider or think at, is the fact that we're seeing a weak negative Pearson coefficient for both the medians in the 1 week window and the 2 week window, almost at 0.5, and 0.4 negative, that of the maximum of the solar wind dynamic pressure, aside from that of the maximum dynamic pressure in the 1 week window. This is an interesting point because this is agreeing with the saying agreeing, but showing a similar relationship that we saw from that of Jasinski in 2025, which showed that the solar wind, despite increasing in pressure, we were still observing decreasing temperatures. So perhaps there is something that's there, or at least agreeing. But is it a strong relationship? Not particularly. What was even more head-scratching was when we considered the set in January 2026, which I want to stress is only 4 data points. So as much as what we're seeing here, it looks really interesting and certainly starts to agree with that of Masters in 2024, it's 4 data points, I want to stress. But it is interesting in the fact that the range of temperatures that we observe is only about 13 Kelvin. It's one of the shortest, ranges that we've really seen when it comes to Earth-based observations, with the mean and the median both pretty much agreeing with one another, probably because of the short range. Completely oppositely than what we saw in August and September, we see a very strong to a weak Pearson coefficient, but a positive one, not a negative one, which kind of agrees with what we were seeing before with Masters, where we saw that basically as one declines temperature, so does the solar wind. So is this perhaps suggesting that the solar wind has some effects at particular intervals? Perhaps, but overall, in usual ground-based observations, we still need a lot more work to try and decipher this. At least on a shorter term scale, we need a lot more dates, was kind of the main gist from this. The concluding points, at least, were that we did see very similar temperature fluctuations that were seen back on the same number of days as Millen et al. In 2013. So that was certainly reassuring. In January 2026 presented one of the tightest ranges of temperatures that we've ever seen over a month, which align pretty closely with temperatures observed by both by James Webb. That's what you're seeing here on the right-hand side with these yellow dots. Basically, they cover between 390 and 402 with not a lot of variability. So that was assuring, but also perhaps suggesting that the observations that we saw may have been a unique event, or equally highlighting that perhaps it is the effect of ground-based observations that have been the main cause of perhaps some of the shorter term, so 1 or 2 day variability that we've been observing. It's something that I'm hoping to kind of continue investigating and using James Webb to try and identify if this is a possible factor. That's not to detract from the fact that certainly the decline on the longer term range is still something that we observe presently occurring. When comparing our stuff, along with both with Henrik's, which again you're seeing here on the lower right hand side, looking at a 1 week window and 2 week windows, we similarly see from our results from 2024 to 2026 that the Pearson coefficient, when comparing to that of the solar wind dynamic pressure, is on the similar orders of about 0 coefficients. Again, strongly agreeing with not only our dataset but with Millen's dataset that we do not observe over the 1990s to 2020s a correlation with the solar wind effect or solar wind dynamic pressure. But both of these methods have only used the tau model. We definitely need to do more solar wind comparisons, solar wind model comparisons in the future. So I'm hoping if anyone would like to always reach out on any solar wind models, especially those that can go all the way out to outer planets and Uranus, that would be incredibly helpful to do further investigations. And certainly, if there's any recommendations on different parameters, typically at the outer planets, we stick to using the dynamic pressure. Certainly, I know the velocities are pretty much constant out at those 19 AU points, but if there are other parameters that anyone would suggest, those would be highly recommended. Otherwise, yeah, that's pretty much everything. Thank you.